PhD outcomes is, as all PhDs are, it's a long and tough journey. And this really is we're hoping a game changer in ore characterization, precision ore characterization. And we hope this will excite the audience out there as to how far we've got in understanding consistent measurement of ore properties. So Shujaat came to me as an excited young student. He left as an excited young student, so that's good to see. He's not worn down. Got a job immediately, which is even better. And Shujaat's really active on the GCC. Has been with the junior leadership with ALT group, is helping organize events, and is moving up to being an associate member now. So this is kind of his launch into being a full GCC member seminar. So welcome, Shujaat. Over to you.
Right. Thank you, Malcolm, for a generous introduction, and truly appreciate it. Always great to present from GCC platform, and yeah, it's good to see developments out there. I also want to thank everybody who is attending the seminar today. And look, I think it's a big shout out for my advisory team who really made it happen. It was not only me. It is the support of you all, including Malcolm, Mohsen, Dion, and Grant. And now coming without any further delay into my PhD topic, that what I did, it's me sharing my outcomes with you all, really focusing on the development of a novel ore characterization method so that we can quantify practical minimum energy requirements for the breakage of rocks. And the concept that we used was size-specific energy. And the only trick was basically to how precisely we can measure that size-specific energy so that we can then use it for benchmarking or for assessing our comminution circuits, right? So on today's agenda, I'm going to walk you through providing you a bit of context on the rationale, what was the rationale behind So what was the rationale behind this research? What was the motivation? And then I will hop on to a bit into the development of the method. And then finally, I will share the outcomes with you all based on the ores that I studied and the site where that method was assessed upon. Okay, so now how I go to the next slide there. Okay, cool. Comminution, or for audience who do not know what comminution is, it's just a process of rock breakage. No surprises, I guess. It's in the entire mining value chain. It's a highly energy intensive process. Pulling off some statistics and looking at that, at around 36% of the overall mine energy consumption relates to comminution. And that's really a big number. And look, I think any little improvement opportunity brings us an incentive in terms of energy savings. And there, so I mean, in terms of nowadays, especially what carbon emissions cut and environmental constraints that we have in kicking off our mining operations or for brownfield operations, it's of really great value. So what we basically need to do, how we do that. So for that, we need to identify opportunities if there is any improvement opportunity sitting out there. So the underlying thing in that case would be we need to know what's the performance of our circuit, right? And we need to know that efficiency, how we do that. So it could be done in two ways. One is the theoretical and another one could be the practical. So when we say theoretical, many people have come along, respected researchers, and they worked a fair bit in that space using the concept of surface free energy. That's really the energy just to break sort of bonds on the surface level between the rock particles in their structure. So they are somewhere sitting around on average 1% of energy consumption. But it's really a hard benchmark or hard target to achieve, and which is why they have not come to a consensus, and this has been into various controversial arguments that it's not easy to achieve and it's impossible basically. So that laid down the foundation of we need more sort of practical methods, and that's where other methods come into play. But as I was telling you, why is that hard benchmark? Because literature suggests that your particle actually needs more energy than theoretical, that just surface-free energy, which theoretical estimate is taking into account. It has another component, which is strain energy. It has losses, and it has crack propagation energy that goes to it. So specific practical energy is essentially constitutes all these components. So you cannot just say that we use surface-free energy and when we provide you a theoretical estimate. So then coming to the practical methods, again, there are so many of them out there, and for different sort of equipments, many people have been coming along. They were inventing just another method. And what was the reason for that? I'm going to tell you, because the first thing is that those methods are really, really empirical. When I say empirical, I mean, I'm talking about two widely known methods. So the first one is bond method. Great method. I mean, works really well for the purpose for which it was designed for in the first place. But any application other than that, it tends to fall apart. For example, I'll just provide you a very holistic view of one of the flaw of the method. If you apply bond method to assess SAGML performance, it will mislead you. So you cannot really trust on that. Likewise, you have Morel method, which is established or developed based on a large database of the existing circuits. But it really raises a question that, okay, it's a good method, it's doing the job, but those circuits in the first place, were they performing to the mark, to the top of the line? No, nobody knows about it. So it raises a question that we really need to go back and start thinking, what is the practical minimum or on which our circuits should be operating, right? And that again begins us think that, okay, why does that happen? Because those methods cannot isolate the effect of the grinding environment when they test a rock, when they test an ore. And at the end of the day, we are always interested as a mineral processing engineers or practitioners, we need to know the energy of a rock. We are not interested in whatever is the grinding environment, right? And that's where all those methods struggle actually. So also direct energy measurement is extremely challenging. It can happen up at the coarse particle size range if you use some compression test or something that I'm going to talk about further on. But applicability of a single method to cater for all these requirements that we need, it's so hard, and it doesn't exist, right? And on top of that, other things are there, extremely laborious, expensive, and large sample sizes are needed. I'm talking about good something, for example, drop weight test, 200 kilograms per sample. So if somebody is actually interested to see that what these methods are capable of and what they're not capable of, where they struggle, so I have critically reviewed all of them in my thesis. So that's just there down the title of my thesis. So a crux of what I just said in my last two slides. So we have theoretical absolute that is so hard to achieve. It will not be wise to just chase the tail of that because we cannot achieve that, never. And on the other hand, we have the empirical methods which are misleading and not effective. And likewise, other shortcomings of them listed there. What is needed there is basically a method that sits in between and that provides us the more realistic estimate of our comminution energy. When I say more realistic estimates, you remember we have where I showed you all the constituents of our rock fracture energy. I'm talking about that. Give or take some losses and bring us to the reality of the rock breakage energy. That's where we're interested in, right? So we need that. And for that, we have to have an ideal test developed. What is an ideal test? I think if we look back at the literature, Shaunet clearly demonstrated 1971 that single particle breakage, if it's done in a controlled way, is the most effective way of breakage, right? And if you manage to get accurate estimate or measure of rock fracture energy on single particle breakage, you are winning. That's good. And if you can then apply that to wide particle size range, that's even better. Why? Especially we're talking wide particle size range is super important in the fine sizes, because we are looking at the Hooke curve that really emphasizes that energy is relatively marginal on the core size range, but it really kicks off exponentially at the fine size ranges. As you see, it went at around 100 microns straight from 2 kilowatt hours up to 20 kilowatt hours done. We see that, right? So this is important that our test needs to cater for those fine size ranges as well, right? So if we manage to get this kind of test, then definitely we can benchmark all of our sites against that, and we can uplift their baseline performance. Really quickly walking you through single particle breakage tests that are already there. It doesn't mean that nobody came up with this idea of single particle breakage testing. Many of them are there. Let's see where they fall apart. If I were to break a particle of 100 micron at around 0.3 kilowatt hour per ton, how much, and if I'm using any of the tests that are there on the picture, for example, if I use compression, so I need to displace the jaws of my compression device by 5 micron millimeter, 5 micron meter with 0.5 microjoule energy. Can you imagine how small is that? So it means we are talking something good about 13th part of the thickness of our hair. So the average thickness of our hair is around 65 micron. So it's practically seems impossible. Likewise for drop weight test, we need to drop 100-gram ball from 5 micron meter distance. So it really basically gives you that sort of knowledge is to make sense of things in your headspace, that how does it happen, and it cannot happen practically, right? So then there is an alternative way of doing things. So that we call size-specific energy, right? So has been around for a long time. We define it as an energy to produce fines below a certain marker size. So marker size is basically just your nominated size, product size that you choose, and everything below that, basically energy that you consume to produce material below that marker size becomes your size-specific energy. Was used first in 1919 by Davis, and then since then, people have been working on that. But it was really when Professor Malcolm here in the audience, he formalized the concept of this and brought some really groundbreaking research. And then Grant took the lead, and he worked greatly on that. So what you see out there in the graph or in the plot, there is a typical size-specific energy curve. X-axis showing you specific energy, y-axis is a generation of your fines material. And if you plot your particles, you fit a line and you force it to pass through the origin, the inverse of the slope of that line will basically give you the size-specific energy number. And the beauty of this method is, to be honest, like you can apply it for industrial devices, lab scale devices, because every method will give you sizing data, every method will give you energy that you input there, right? It provides you then a good way of comparing your circuits or other laboratory methods against the ideal test that we are talking about. So that ideal test is really missing that data that you see on this picture there is because there isn't one method that can generate that data. And we need to come up with method, and that was the rationale behind my PhD research, that if I am able to develop a method that will populate this data, then we will be in a position to benchmark our circuits against that. A student of Grant Valentine, Reja, he did a great work, groundbreaking work in this space. So what he did, he knew that using single particle, you cannot generate enough fine material, and it's so challenging. So he instead basically broke a layer of single particles equally spaced, and he proved that, well, if you break monolayer of particles, you can still get a result similar to single particle breakage, right? So good enough, I mean, a good motivation for me. And similar work was done at Professor Marcelo Tavares' lab in Brazil. And that is also very good work that basically built the foundation of my work going forward. And what I did was basically that if I managed to get a device that breaks a monolayer of particles in a very controlled manner, and I managed to get enough fines for sizing, right? And also I can measure the breakage response accurately using some kind of torque energy method, I will be in a position to determine my practical minimum comminution energy across a wide particle size range, right? And the word that is important here is controlled. And how can we control that? I'm going to talk about that further. So this is the device that I basically used as a guinea pig for my PhD. We call it precision Rolls crusher. It's essentially a fixed gap Rolls crusher. We got two rolls counter-rotating. We got a feeder up there that is really specialized, fabricated for sending a monolayer of feed right in the middle of our rolls. That is guided by two guides that you see there on the screen. And the breakage response is then recorded using highly precise torque sensors that are mounted on the shafts driving your rolls. And then you use that data of response and torque that you basically log, plus the RPMs of the rolls, and then you calculate your breakage energy, right? Also, another cool thing is that we added a sample cutter here. So when you break your particles, you can also sample your product progressively when you reduce the size of your feed. And that gives you good information of energy plus your product. And just to say that the equipment that we have at JKMRC is currently just for research purposes. It needs a further upgrade to be applied like commercially. Okay, so the method, what was the method? It's basically, as I said, it needs to be controlled. The breaking needs to be controlled. How do we reduce the size? We use the method of stage-wise breakage, what it is actually. So we choose a particle top size, a feed of certain top size, right? And then we control a gap. So we then control a reduction ratio between the gap between the rolls and the particle top size or the feed top size, right? And then we keep it constant. What do I mean? That, for example, if we choose a particle top size of 9.5, I keep my reduction ratio 0.8. When I will break it at a fixed gap, so of course this is just a ratio 0.8, I will get a new product size. That will become a feed size of now my next stage, because I'm doing a progressive breakage. Whatever product I get, I send it back to be broken again for the next cycle of breakage. And I keep doing that on and on until I achieve my final desired product size, right? So, but when I do that, I keep my reduction ratio constant between the passes, and then I go all the way to the end. And during each stage, I measure my breakage energy. And that reduction ratio that you see here is chosen. There is a study behind that as well, again, covered in my thesis. It's just that minimum reduction ratio that just fractures particle gently, does not overbreak. Okay, so a bit on energy measurement. As I was telling you that we have highly precise torque sensors, around 10,000 samples are captured per second whenever there is a breakage event. And then we use that data to calculate our net torque energy. So what's important here is net torque energy that you have if you look at the graph here, so you get your gross torque energy. If you accumulate your energy for all the events of breakage, because there are so many particles being broken at the same time, so you just need to accumulate that energy all along. And if you do that, you will get something trend like that, and we call it cross energy. So the reason you're getting this trend there is because there is a background noise there. So what you need to do is basically to eliminate that noise. For that, you need to discount the no load energy or no load torque. So how we do that, we run pressure empty in the beginning, we log our data, we calculate our no load energy, and then we discount that average no load energy from all the data that we log. And then we do the cumulative. And this area under this curve gives us the total energy for that entire size reduction. And this is basically, you can just read off the value. So this is how we do it. Again, procedure here, what we do, it's a stage-wise breakage, right? So during each stage or each pass, we feed our monolayer particles, we break, and then what we get is a product. We size that product. In the meantime, we also measure torque, energy, RPMs, and then we calculate our energy, breakage energy, and then we reconcile that our mass data of our product, and then we calculate our size specific energy and specific energy. And yeah, the same goes on for each stage of breakage. So now coming to the application of the method, we studied two sites. So the first one was basically a site where you can see that a flow sheet has an array of equipment. It's a copper gold ore from Australia, also again covered in my thesis. And hard rock ore, what we are basically interested in here is that an experienced team of researchers from JKMRC, they did a survey back in the day, and really high quality survey there. The stars are showing you the sampling points there. We had the sizing data, we had the throughput, we had the power, and then we calculated on-site energy from that with a good trust, because that was a repetitive survey. And so the ore A, so altogether we used 3 ores. Ore A is coming from site 1, and then we got 2 ores, ore B and ore C coming from site 2. And this study was, and the survey was conducted by one of students from JKMRC. I think Jeremy, many of you may know him. So he got his thesis published recently as well. Yeah, he went out there and he surveyed. And I also got this data from his thesis and then used that. I also had the samples, tested the same samples on my equipment as well, and then benchmarked those sites against the precision load pressure. So these are basically some results from precision load pressure. What you see is a suite of size-specific energy curves for different marker sizes. I think I did explain what marker size was. So what you see here is that your your size-specific energy is essentially decreasing with your gap, right? So it is in contrast to the previous findings by Hilden and Suthers in 2010, who say that it is basically size-specific energy estimates are consistently linear across different training circuits. But what I found was that no, they decrease with it. So there are two things to notice here in these graphs is that first one is that why do they decrease? And the second one is that, especially if you look for the coarser marker sizes, especially the light blues, light reds, and light greens down there, we have a kink down the bottom, and it reduces and then it begins to kick off, right? And let me walk you through why does that happen and what are the answers to those two questions. All right, the first one is that why does my result were decreasing, my site-specific energy was decreasing as a function of gap. I think, and similar results were obtained by Grant and also by Reja, who was a student on short impact load cell device, and JKRBT plus Shonet device in case of Valentine. And we are all agreeing on one thing, that this happens because of the reduction ratio. There is an influence of reduction ratio. What does that mean? When you have a fixed product size, for example, in our case, 75 micron or 106 microns, so then we are consistently reducing our feed size when we are progressively coming down towards the size reduction. So it basically needs less energy when you reduce your reduction ratio, right? So this is a work from Forestino and who showed this proof. We use that as an evidence for our study as well. And another thing that I was telling you, that why there was that decrease down at the bottom of all of those graphs. These are basically those kinks that I was talking about. When you have so many of energy curves for different marker sizes, we have an objective that we are interested in practical minimum comminution energy. What is that practical minimum comminution energy? That is also another question, right? So we all sat together and we decided that we know what that is. And I'm going to tell you what is the story behind this game. So when we come down, keep decreasing, we come to this point, and then that's the asymptote where the slope becomes zero. After that, it begins to kick off again. So this range is basically inappropriate marker size, because you came to this point down here, let's say talking for 300 micron size. So when you came down here, you already have produced your product of 300 micron around 80% or 100% passing, right? So you have basically produced your product below that marker size. So if you go any further than that, so what you are doing is now, since it's a progressive breakage, do not forget that, right? So now you are just grinding or preparing product for the next passes, for the next marker sizes. So this marker size of 300 micron becomes obsolete. So which is why you see this energy increase back again. So this was the point we were interested in, that this is the end. That's the or practical minimum comminution size specific energy we are interested in. And we were interested in seeing this kind of low or the asymptotic points for all of our curves. Very good, we saw it for 300 micron, for 212, but again, when we are going upward, it's still reducing. Here comes another catch. Why we didn't go further? Because look at the gap where we are operating. We are at 60 micron here on the precision nose crusher. It's a very fine gap. Any further than that, we could not achieve on the current setup of the device. It will need highly precise, highly aligned, very good alignment capabilities on the equipment to achieve that, right? But then what instead I do is that I use this data, because now I know the gap for the corresponding minimum size specific energies for at least 1 to 3 of these curves. And then I try to basically model or extrapolate the gap for my final marker sizes, right? And that is all I'm doing here. I have a gap for minimum size specific energy and marker size. And for all those 3 ores, I'm just extrapolating the gap and trying to find out my another low point so that I can use that for my study, right? And look, there were uncertainties with the when I was fitting the line as well. So we can go even further than this as well, but I just stopped there because of the uncertainties, and I was just unsure that if this is going to be persistent even further down. So I just stopped there, right? And also another interesting thing is that it is these 3 different ores appear to be size dependent as well. So you see these differences. And then the third step was that we had those marker sizes, the known marker sizes, and then I just tried to plot relationship between minimum size specific energy and the marker sizes, and see what is there and how do they basically add up. And I tended to predict it backward as well. So I found a really good power law relationship between all of them for all those three different types. And you see there is a size dependency. It's very interesting that three different ores are basically different from each other in terms of size specific energy. And it's actually product size dependent. It decreases when you are increasing the your marker size, right? And then I predicted my minimum size specific energy using those models there or equations there, and it came in a very good alignment with my measurements. So that gives me a good confidence that we can use this kind of model value or models to basically predict our minimum size specific energy for the unknown marker sizes. Okay, so this is basically application of precision dose crusher on those circuits that we studied. Again, those three typical size specific energy curve, plotting site data versus precision dose crusher. You see that all those equipment from each side are up there. You have ball mills represented as BM and SAG mills, HPGRs, and the overall full circuit up there. Look at the opportunity. I mean, it's significant. It shows that you have a way to basically improve yourself. And as I said, I am using marker size of 106 here just to highlight why. So because to get to the marker size, I would have loved to use 75 micron, but it was a constraint because of the equipment that I could only go down to 60 micron. And at 60 micron, I was not able to get that minimum size specific energy for 75 micron marker size. So, but however, which is why I just like took a step back. I went to the safe side and I used 106 micron, where I could confidently basically say that, well, I can use this data. So that's the very reason I use 106 micron. And same for OR B and OR C, it's the same circuit, only ores are different, right? Or for OR B for side 2. For both of them, again, significant opportunity sitting there. Just another representation of that curve, just to give you a better understanding in terms of simple bar charts, that how we can use to precision dose crusher to rank our circuits. So I have just shaded this area where it's just comparing your circuit against the precision dose crusher for all the side for both sides and for all three different ores. So look at that. I mean, there is capability, like you are using, your sites are using anywhere between 3.2 to 3.8 times the energy what precision dose crusher is actually using, right? So, and if also it shows you individually that which unit actually in your circuit is underperforming, right? For example, if you look here, out of all this, ball mill 1 is the one that is consuming the highest size specific energy, right? So if we bring it back, even if we bring a little bit of improvement, so that would mean you are reducing this energy here, right? So then this number will come down. So yeah, so you can identify underperforming equipments actually using this kind of analysis. And also, not only that, you can also rank your different kind of ores and using that method, using this analysis. For example, or A use 1.8 times energy of OR B and 1.2 times energy of OR C. So really, like if you are running on the same circuit, or even if you're comparing different sites and doing the same kind of analysis, you can say that what is happening, what is how things are changing between different cores, right? And likewise, it's not only that you can test on-site equipment, you can also evaluate other methods, lab scale methods, testing methods, and you can find if they're evaluating or if they are actually performing to the mark that we want. Just an important point to highlight here is that instrumented bond mill is basically exactly the same method for as bond method, but we are using torque sensor to measure the energy, right? And then same way we have a lab HPGR. So look, what I wanted to say was that these are the two methods that we widely use also for measuring the performance of our on-site circuits, right? And then we design them based on these methods. Look how inefficient they are relative to precision load pressure. And then you can automatically imagine that what will be the repercussion of this kind of things then building up and going to the scale-up level, which is industry. So things add up and then you see all these inefficiencies there. Okay, so this is a really interesting one that we found out that efficiency that everyone has been talking about, that, well, this combination circuit is efficient with this number to do different kind of fancy analysis. But what we found is that it is actually pretty much product size dependent. So what I did was basically I calculated a ratio between the size specific energy of different comminution units against the precision load pressure. And then I plotted that ratio as a function of marker size. So my marker size really presents here the product size, right? And this I did for all those three different ores. So what you are saying is that when your SEC ratio is high, right, so your efficiency is lower. So if you are operating somewhere here, so it means you are not doing well. But if you are somewhere down there, so it means you're performing well. So we want to be somewhere in this range, right? Excuse me. So the sites that we studied had a product size range, right? So if you're talking about the site one, so the product size range was somewhere around, I think, 120 to 170 micron size range, because this size ranges are desired because of that flotation recovery, because flotation recovery can only perform well within a certain size range. And likewise for size two, the desired size range was somewhere around 100 to 110 micron, right? But what I want to tell you here is that, look, so at the background, we have these three different curves and showing you the grinding data. Look, where are we sitting up there, right? So we were actually supposed to produce lots of material in this size range, but we ended up producing lots of fines, right? Which is why you are landing somewhere up there. So one important thing to remember is that if you have a desired particle size range, always optimal will be to create a narrow size distribution within the desired particle size range. I know it's hard with the current technology, especially with the like milling technology. It's so hard. You do not have any control on your grinding environment. But it also just gives us an insight that we need to basically look into the modern ways of breaking rocks. And this gray out area is actually just letting you know that this was the marker size that I used, but I still decided to plot this curves below that marker size, just to give you an idea that if we manage to basically make any improvement, so this graphs will basically shift down, but still not to an extent that there will be a significant change here. So there is still like lots of improvement opportunity there. So Grant came up with this amazing idea that he has been working lately on, the fractal dimension. We were seeing interesting results, and he's like, well, we have the data, let's look into it. Look into the fractal dimension. So, oh, yeah, sounds cool. What is fractal dimension? Fractal dimension is basically, it's a mathematical concept that that is used in science generally to basically quantify self-similarity of different sort of patterns, right? For example, snowflakes. I'm just putting down here an example. So it's, if you look at a bigger snowflake, and then if you go further, zoom in, and then you will see the same pattern being repeated, and it goes on and on and on forever. And Turkett, one of the earlier works in this space, he showed that actually, or the breakage, the product of or from the breakage of the rocks actually exhibit the similar kind of behavior, right? Likewise, and then many other people came along, they did research, and from 2019 onwards up until recently, Valentine has been working a lot on that. So the thing that I want to highlight here are basically two of them. So the fractal dimension, in terms of visually, when somebody says that smaller fractal dimension, what does that mean? And they say it indicates bulk splitting. So this is bulk splitting, by the way. What you see in the picture is right. Bulk splitting, I would say that it's more like a sort of Brazilian test style product. Like you really see your product within a narrow size distribution, right? So that's very controlled progeny. However, if you have a wide size distribution, lots of points and also cores, and then you tend to increase your fractal dimension number at this you see here. It has higher fractal dimension number. So I think this gives you an idea of what is smaller fractal dimension and what is larger. So the smaller we refer to is basically, we call it bulk splitting, more controlled way of breakage. Let's put it in that way. Or pulverization, on the other hand, is over breakage or more crushing, and that's cracking kind of environment. So how do we calculate it, right? So up there is this simple equation. You basically plot your site-specific energy against marker size. And in my case, I chose just like this marker size in between it's 38 to 75 micron, because that's where it was a linear section there. I didn't move any further on. Why did I not? It's because it relates to that the rolling off section that explained the inappropriate selection of marker sizes. So, but I just stayed in the safe zone where I could see linearity, and then I measured the slope in a log space, and then I just use this formula, and then you can create it for fractal dimension, and you will see what's the importance of it, what it can indicate. And I did the same for all the O's. Okay, and then I plotted fractal dimension as a function of gap. And this is really interesting, that what I see is that we have a high fractal dimension when I'm operating in the coarse gaps, right? What it is telling me is that when I'm operating in the coarse gaps, so my breakage is not as efficient, or it's not doing the bulk splitting. It has more track sort of formation happening. But as I go further down towards the gap size, right, and it's improving basically the breakage more there, right? And this was obvious. And then there was this point where we had a kick again back up, which is indicating that something has happened there. I went back and I looked at the proofs. So what had happened there was that there was a misalignment between my front and back roll of around 50 micron. And I'm already operating at a very fine size. And so this 50 micron misalignment basically started, messing up with that. And it started again adding to the inefficient mode of breakage. So it really provided, all right, fractal dimension is telling us something that is, and it goes and tells you what is basically, it may indicate facts about what is happening, what is your mode of breakage. Not only that, if you use fractal dimension for different ore types, and you can just using simple, because you just need your product size distribution, and you can still tell a lot that what is going on in your products. For example, if I were to talk about instrumented bond ball mill here and across 3 circuits here, first, let's compare like each of these methods here, what is happening. If you looked at your precision rose crusher at the closing gap of final 60 micron, it has a minimum fractal dimension number. So it is telling us that your precision rose crusher has the most controlled way of breakage. It's the most efficient way of breakage, which is why it is giving us the minimum practical energy, which is why it's consuming the minimum energy there, right? In comparison to other methods. It's just the data that we got from particle size distribution, no energy yet. It is still indicating so much to us. Another thing is that our lab HPGR has higher fractal dimension in comparison to ball mill, but in smaller than the circuit. Why? So because lab HPGR has like really sort of, you do lots of compaction there. It's a bed breakage and you create lots of cracks. So lots of cracks means it's your fractal dimension number just exceeds. And when we go to the, let's say circuits, let's talk about the main circuits, why they have the highest. So you have a circuit like lots of crushing and grinding mills in series and breakage mechanism there, right? And also when there's lots of regrinding happening there, especially due to poor water split in your cyclones, hydrocyclones. So they send lots of fines that are supposed to go to the overflow with the underflow, and they go back and they keep regrinding and stay in the system. So that increases your fractal dimension of the product, right? And again, same in the ball mill, a very similar kind of overgrinding concept because you don't have much control there. So this provides you a bit of context on that. And then likewise, you can compare different project across. Okay, so last few slides. Yeah, I think where are we looking with this method actually in future? So a way forward is to really link the site-specific energy that we got from prescient dose pressure during our progressive breakage and relate it to our liberation data, because isn't it the liberation that we are looking for at the end of the day? Because we are grinding for recovery. So we need to recover that, liberate our particles so that we can recover maximum out of it. So if we take lots of samples and then we do just core splitting, a part of that we send for analysis to geological analysis. Then another one, just we can use that and we can crush that in a jaw crusher, create ourselves good splits of our samples for as a feed to our rolls crusher. And then, of course, as I said, in rolls crusher, you start with somewhere in my study, I started somewhere around, I think, 8 millimeter or something like that. And then you can go all the way to the fine end. But while you do that, you have your products, progressive products. And for each of those products, you also have site-specific energies related between each of them. So what you can do is actually you can send off those samples for liberation analysis, call it QMA, mineralogical liberation analysis tomography, and then you relate that or do some analysis and link that to the size-specific energy that you got for those products, and you can get a lot out of it. And it's a simple test, just like a little sample. Then you can use that information and populate your block model or geological model, and not only with your energy, but also with your data, mineralogical data. I think that's where we are looking with this in the future. And I will be extremely happy if someone comes along and take this up and applies this kind of things on that. Takeaways from today's talk is basically, of course, no surprises now that I did prove that it is the most efficient way of breakage to determine practical minimum energy, at least at this point, unless somebody else comes along and find another method. Well suited for identifying underperforming circuits and units. If we use this method and determine site-specific energy, we can definitely do that. Under the same conditions of breakage, the fractal dimension can be used as an indicator of ore competence. As I said, that fractal dimension may indicate a lot about your course, and of course, in terms of ore competence. Also, I showed that how comminution efficiency was product size dependent. So next time if somebody comes to me and says this number, I would say, at least I would argue that actually, no, it's product size dependent. And the last one is basically, we can use this for potentially for variability programs and geomet testing because the method is simple, quick, and it requires small sample size. So before I conclude, I think people that you see on screen, they mean a lot to me. I think they deserve a big shout out in my personal development, in my professional development. They have invested their time, efforts, and from them, I think from the middle of nowhere, I had those times. They created opportunities for me from thin air, and I truly appreciate your support to all of you. If you are in audience, yeah, extremely thankful to you all. And then I'm thankful to JKMRC management and pilot plant for their support. And of course, it's never possible without family and friends. So yeah, I will just stop it there. Thank you so much. Over to you all.
Thank you, Shujaat.
Oh,
Go ahead,
Shujaat,
Mark.
same one.
Right.
So really a good fly through of 4 years of work, from the technology to what underlies it, to what you measure, to how to apply it, and maybe the future. So I think that's a good platform for people to ask a whole lot of really difficult questions. So opening the floor to questions, you can put your hand up or speak out. I saw there was one in the chat.
Yeah.
Can you see the chat, Shujaat? Do you want to answer that first?
Yeah, I do. So the question is that I'd be interested to know the opportunity with stirred mills, as they can be more efficient than ball mills if operated with the right media and speed. Do you have any thought on that technology? So Steve, no, I do not have any data on stirred mills. Also, I think that would be really fine grind size. And I can only comment that we would need technology improvement. I'm not talking about stir milling. I am talking basically about what I developed, because if you remember, I really mentioned that we can only go down to 60 micron, but to test that kind of product against the precision nodes from the stir mills against the precision nodes crusher, we really need to go down, touch down the boundary somewhere, I think in 20 micron at least. So we need to basically.
Yeah, sorry, I was thinking of that chart that you put up, Shujaat, where you compared. I guess you compared the theoretical energy size with different technologies. You had ball mill, HPGR, etc. Exactly this one, and you talked about the opportunity. But I was hoping to see perhaps a stirred mill somewhere on that blue, on the purple curve. But I guess you don't have the data at this stage, huh?
Yeah.
So Stephen, there was some good work done by Sam Palionandi, and he went down to stirred mills and he used a finer marker, 25 micron. He also tried some test work based on Hardgrove Mill, which Frank Shee had done, and he refined to try and get this ideal number, but didn't really succeed on the ideal number. So we kind of parked that. So he has some data going down the curve, and you can see how the stirred mill moves. But as Shujaat says, that's the next challenge in the device construction, is getting one down to super fine gap. Definitely in our aspiration.
Okay, gotcha. Thank you.
Welcome.
Shujaat, I have a question for you. And you presented the relationship between the relative site-specific energy for the three ores in respect to the market size, I think.
This one?
No, there's another one that you presented. I think it was
this one.
This one. Yeah, this one.
Yeah.
Just to understand the trend you presented, because it seems that when you have finer sizes, you have the lower size specific energy, but it seems to be the opposite trend I was expecting, at least.
Here?
Yes.
Yeah. So that's why I put this thing there. In this marker size range, the PRC has not achieved the actual minimum size energy yet.
Okay.
I think that answers your question.
Yeah.
So this should have been somewhere up there, right? So yeah, you're right, on the money there. So if I was able to achieve minimum size specific energy there, so you're right, it should have basically went up.
Okay.
Yeah, good question. Good catch.
Thank you, Shujaat. Very interesting presentation.
Yeah, cheers.
I might throw in another comment on that. It also, although Shujaat's pointed out the limitation to that graph, to For me, it indicated that the circuits were set up to be more efficient at grinding finer than they needed to. So they were off the efficiency regime. They should be targeting coarser, but when you put it in a SAG and a ball mill, it just grinds finer. You can't stop it. And I think that's what it's telling us, and it's pointing the direction to improve efficiency if we actually get the circuit lined up with the product we need.
Okay. So, any other questions? We still have time.
Were all those tough questions I was expecting? I've got just 2 tough questions so far.
I could do a question. What sort of precision are you getting on the gap between the rollers? Considering, I mean, how you're adjusting them, playing bearings, concentricity, and all that.
Yeah, so I think I have added the number in my thesis, but I think like on top of my head, somewhere plus minus, especially in the fine size range, 20 micron. Was that 20 micron? Plus minus.
Yes, 20 micron per roll.
Yeah. 20 micron per roll. So yeah, I think that really basically shouts at us that we need to improve that, and which was the very reason we just stopped there. And that roll started sort of colliding with each other almost. So
yeah, fair enough. Thanks.
Yeah.
Great presentation, by the way.
Yeah, thank you.
Hi, Shujaat, Jeremy here. Just yeah, fantastic presentation. Thanks for taking us through what is a really remarkable piece of work.
Thank you.
Just, I suppose that ratio you used on the reduction in each batch test as you're moving through, was that ratio modified, or was that fixed in all of your work? Do you think it's sensitive to the minimum comminution of energy of the precision rolls crusher? Do you think it's sensitive to that ratio? Was that varied in your work or consistent? Just a question.
Great question, Jeremy. I think in my work, I kept it 0.8, and there was a reason behind that. The reason for that was that was the very reduction ratio where I was achieving just that little fracture that I wanted. And how did I basically set that reduction ratio? That could have also been an added question there. I basically validated that reduction ratio against the device called short impact load cell, right? So what did I do? I basically broke the same ore type on short impact load cell that apparently gives you primary fracture energy. And I broke like population of particles. I had the energy from short impact load cells. I did a sizing distribution. I also knew the energy. And then I started changing different reduction ratios or applying different reduction ratios on the same feed type, on the same particle size in my precision rolls crusher. I moved back and forth. And 0.8 was the reduction ratio where I came to a match or close match with short impact load cell progeny, and also with the energy. So which is why I chose that, and I kept it consistent all across. Yeah.
Thanks, Shujaat. Excellent answer. Yeah, that clarifies it.
Yes.
Any more questions out there? Last chance before we close off. Well, thanks, Shujaat. That really was a good overview. Well done on that. And we hope that this can reach the objective we've had for some years of this moving into a standard characterization method, and that it should be really illuminating to us practitioners out there that we're using around about 2.5 to 3 times of the practical energy that we should be able to achieve for comminution. So there's a target to go home with. Thanks, everyone. Thanks, everyone, for joining us.
Yeah.
Really good to see a
Thank
good
you,
turnout.
everyone. Yeah. See ya. Welcome. Get well
Thank you,
soon.
Shujaat. Yeah.
Cheers.
Cheers,
Bye.
everyone.
Cheers.
Bye.
Bye.
Thank you.
Thank you.
Thank you very much.
Thank you.
Yeah, thank you.